Hello students, welcome back. Let's go to section 3, integral constants. Here's a motivating example. Y prime, the derivative is given as this function. And we have initial value, y of 0 is -1. Using these, I have to find out the original function y of t. This is an example of a differential equation, as a matter of fact. An equation related to the derivative and differentiation, and I'm looking for the original function y of t. That's an example of a differential equation. But it's a really simple one. Derivative's there, so all you have to do is to take the antiderivative, and let's go ahead and do that. Take the antiderivative. Y prime is t e to negative t squared, so take the antiderivative, and we get this. By the way, how do you take this antiderivative? Let's have a very brief review on integration by substitution. Take u as the inside and look at the derivative of this. Derivative is negative 2t. Does it show up here? Yeah. We have t here. Indeed, this is the substitution by this is the integration by substitution. U equals negative t squared. Take the derivative and solve for dt, and then substitute these back in. E to the negative t squared is e to the u power. Dt is this. Negative 1 over dt du, this one. And then we have this t and that t canceling out. And what do we have? We have a u integral. Calculate the u integral and then substitute negative t squared back in, and that's what we have over here. Okay, that was a quick review on Calculus 1. But this is not the end of the problem here. I have to find out y of t, and I have infinitely many candidates of y of t because this c is arbitrary. So how do you do that? Use this, which we call the initial condition, and we can determine c from there. So when t is equal to 0, function value is -1, so plug in t equal to 0, and that's equal to -1. So what do we have? We have an algebraic equation of c. So c is equal to -1/2. So c is equal to -1/2, plug that in over here, and there goes the solution. This kind of problem is called an initial value problem. And this thing is called the initial condition. This kind of thing is a differential equation. Derivative and some equation related to derivative. But of course, we're going to do something far more complicated in this course. By the way, in Calculus 1, I never care too much about getting C. If a student misses and does not write plus C at all, I did not take off any point in Calculus 1. If the student missed dt or dx or something, yeah, that was a deduction because that is related to substitution. But plus C, I never cared. Here, I have to care because as you see, it plays a role. It is related to initial condition, and then we have to determine C and plug it back in. That's how you get the unique solution. Here's another example. This time we have the second derivative equal to something. Again, it's an equation related to derivatives, so it's an example of a differential equation as well. We have two initial conditions, y of 0 and y prime of 0. And is it really necessary? Yes. Second derivative is given, so I have to take the antiderivative twice. Each time I take the antiderivative, we have integral constant. This is what I'm talking about. Take the antiderivative, and then we have plus c. And then we can find out what that plus c is from this initial condition. Y prime 0, 2. So plug in t equal to 0, and that's equal to 2. So we have an algebraic equation of c. C is equal to 3, so plug in 3 here. And that is a derivative function, y prime. By the way, how did you calculate this integral here? We use integration by parts. And here we go. U is t v prime as e to the t power. So this one has really strong tendency to become v prime over dv. And polynomial is middle. And logarithm has the strongest tendency to become u. And then u prime v, and then put everything into the integration by part formula. And what do you get? Multiplication, and then this is simple integral. In the end, this is the antiderivative by integration by parts. And then determining c, we got it. But that's just y prime. In order to find y, we have to take the antiderivative again. We need two antiderivative computations. And we need another integration by parts. And then we have this plus b, because I use up c. And I don't want to use d, because d may look like derivative. So I'm using b. And then let's solve for b from the other initial condition. It's an algebraic equation, solve for b, and we have plus 1, and that's about it. Plus 1, and that's the end of the problem. So, in second order differential equation, typically we need two antiderivative computations. So we have two integral constants, so we need two initial conditions, so that we have two unknowns and two equations. Another example of two unknowns and two equations. This kind of thing is typically called boundary value problems. Okay, y double prime, second derivative is given as certain function, but instead of y of something and y prime of something, we have y of negative pi and y of pi. And most of the time in physical system, when we have this kind of differential equation, we are interested in t value or x value in between negative pi and pi. Beyond that, usually we are not really interested. But this is math class, so we can go beyond. But still, because of that physical system and historical reason, it is called boundary value problems, even though these may or may not be boundary. Anyway, calculate the first derivative by taking the antiderivative, but I cannot determine c because I don't have any y prime to plug in. So what do we do now? Well, what choice do we have? Just leave it at c and then take another antiderivative. Because I don't have anything to plug in. So okay, take another antiderivative computation, and then another integral constant follows. We have cx plus d. Okay, alright. And then plug in this and that. We're going to get two equations and two unknowns. Plug in negative pi, we have one equation. Plug in pi, we have another equation. Two unknowns, c and d, and two equations, we can solve it. And what did you get? D is negative 1/2, c is negative 3 over 2 pi. Therefore, we have the solution. That turns out to be the solution. You can check it with computer algebra system. Y of x as this function, and then I'm asking Mathematica to calculate the second derivative. Does it turn out to be negative 4 sine of 2x? Yes, indeed. And how about the initial, or excuse me, boundary condition? Y of negative pi and y of pi, they are 1 and negative 2 respectively. Yes, indeed, 1 and negative 2 respectively. You can check those like these. So what's the moral of the story here? How to deal with integral constants? Well, integral constants were no big deal in Calculus 1, but here in differential equation, they are a big deal. I have a little bit of time left, so let's talk about piecewise differentiation. Not humongously important topic, so let's talk about it anyway. Believe it or not, this calculation is wrong. Correct it. What's wrong here? Antiderivative of 1 over x is log of x, but inside of the log had to be positive, so we need absolute value. What's wrong with this? I don't see anything wrong. As a matter of fact, there is. Because log of 0 is undefined, we have singularity. So greater than 0, less than 0, they are completely separate. So we don't always have the same constant. Log of x plus a and log of negative x plus b, where a and b are different instead of just c. This is perfectly good solution too. And this is more general. So in this case, we took only one antiderivative, but two integral constants showed up. And that depends upon where we have the initial condition. For example, initial condition, when x is 17 is given, then we're interested in only this part. This one we don't, because if you plug in x equal to 17, I'm not going to get anything here. Now, if you have initial condition as x equals to negative square root of 5 is given, in that case, I have to use this one, the lower one, because that one makes sense. I cannot plug in negative number here, but negative number here, so negative is positive, that makes sense. Similar thing goes over here. At x equal to 0, this expression does not make any sense. So we have singularities, so x is greater than 0 versus less than 0 are completely different. So it is not a good idea to have the same c in general. So we have two constants a and b, depending upon whether we have greater than 0 or less than 0. And we have the same antiderivative function. Still, we can have two different integral constants.